Hello everyone, my name is Yonghao, a PhD student from Simon Fraser University, supervised by Xing-Dong. Today, I want to talk about WooDowel, which enhanced triboelectric plywood sensor with electromagnetic shielding. Let's start by talking about what a smart environmental is. Let's thinking about we're living in a smart world, like walking into a house where the temperature is just perfect, lights adjust to the time of the day. This isn't a scene from the movie, it's reality made possible by smart home technology. The heat sensor can detect temperature fluctuations and autonomously regulate the air conditioner, while the light sensor assists adjusting the brightness of your lighting. And also, safety is a priority in any home. Smart environment offers enhanced security with devices that can detect and alert homeowners to any unusual activities, be it an opening windows or an unexpected visitors, ensuring the peace of mind. Additionally, healthier. Everyone care about their health. If you're using a smart table or chair, they could remind you to stretch after sitting for too long, fostering regular movement. And some smart earphones can automatically block out harmful noise, protecting your hearing. And also, a smartwatch equipped with multiple sensors can alert your or your families to any irregular heartbeats. Harrison Chris and Scott Hudson introduced scratch input, a technique using sensor to detect the sound of a fingernail on surfaces, like wood or fabric, turning everyday objects into interactive areas. Besides that, a bunch of papers doing research on ad hoc sensors to help people create a smart environment. All these tools is about equipping your home or office with varied gadgets and sensors that connect to the internet, along with automatic system and data analysis tools. These make your space smarter, but upgrading an existing building can be challenging and expensive. You need to invest money and have tech skills to integrate the new technology with the old one. But sometimes ad hoc sensors have negative aspect. It is useful for immediate and short-term needs, but sometimes there are some issues. Sometimes they might not look nice and can clash with what's already over there. They also might not work well with the system we already have. And another one, sustainability. More sensors you add on, the greater challenges you face in terms of both costs and design aspect. And ad hoc sensor need customization. The reason ad hoc sensor may not always be suitable is due to their inherent need for customization, which lead to specific designs for each different scenario. And in some case, smart material better. The first one, large scale. Imagine adding one sensor on one table is easy, but adding a million sensors to a million table is crazy, right? Why not automate and streamline sensing functionality? And another one, flexibility. Consider using a versatile material for constructing objects. By utilizing this material, we do not need individualized design for each item. Instead, we simply construct and done. And another one, low costs. The mass-producing smart material, we can process a single material in various ways to meet diverse needs, thereby reducing costs associated with both production and utilization. And OptiStructures, which was published in 2020. They're building interactive devices on a large scale, including furniture and entire rooms. Their innovation by embedding input sensors and display into materials like concrete and resin, utilizing fiber optics for both sensing and display purpose. You can use this material to build whatever you want, include wall and table and other things. And 2 years ago, our lab published a paper called iWood, an interactive material made from the plywood. The material can sense vibrations, able to recognize user input as example daily activities. Again, by combining this sensor technology with plywood, the material owns sensing functions and it can be used to build anything, including furnitures, architectures, and structures, just like normal plywood. Utilizing it in constructions made the house automatically become a smart environment. And building on that work, we created WooDowel, a novel approach to address short-circuited electrodes and triboelectric vibration sensors embedded in a smart plywood. Our goal is to ensure the functionality of the senses during the woodworking operations that involve the use of nails and screws. It works perfectly in real life, thanks to the shielding layers that avoid interference with electric equipment. Additionally, we redesigned the sensor layer structures to reduce the possibility of the short-circuiting to zero. And this is what looked like for our prototype. We are using our material to build a table for testing performance. You can cut this material as you wish, and we also ask expert woodworkers to help us build the prototype. They're using drills to pre-drill the holes and using nails and screws to combine the table leg and the table top together. And our table can sense different kind of activities like writing, erasing, drilling, cutting by jigsaw, typing, and play music by a speaker. And basically, WooDowel is similar with the iWood, based on the structure of triboelectric nanogenerators which can convert mechanical vibration into electrical signal. The current state of our sensor design employs no overlap electrodes to detect the vibration via the triboelectric effects. The design effectively mitigates short-circuiting issues caused by nails and screws. But however, signal strength and clarity suffer, especially in real-world scenarios with electromagnetic interference. As a result, the sensors struggle to accurately detect common daily activities. Like you can see from the video, there's no big difference between writing or not nearby an electromagnetic interference environment. So, to combat interference, shielding layer can be added, but this conflicts with initial goal to avoid electrode overlap. Our solution allows woodworkers to manually disconnect the affected electrode by moving special design dowels that interconnect the electrodes. As you can see here, before replacing the dowels, shielding layer and electrode layers are connected with each other. But when short-circuiting happens, dowels will be replaced and the shortcut electrode will be isolated. Each electrode in the plywood vibration sensor is interconnected through the corners via these connecting dowels. And after replacing the dowels, like I mentioned before, the electrode will be isolated. These dowels not only facilitate the connection between neighboring electrodes, but also ensure proper shielding against electromagnetic interference by connecting the two shielding layers. And we've also designed a power jack dowel for easy wiring the sensor to external electronic like our short-circuiting detector. A 3.5mm headphone jack is used here combined with our power jack dowels to make signal output easier. And from the video, the short-circuiting detector here is used for notice people if it happens. Our smart plywood material prototype measures 1200mm in length, 600mm in width, and 25.4mm in thickness, suitable for various woodworking projects. And for evaluation part, we have 10 participants, tested 20 daily activities, and we got a good within-user accuracy, which is 92.2%, and a good cross-user accuracy, which is 86.4%, which means we can definitely classify 20 different activities with each other. Thanks for listening. For more details, please see our paper.